Hey everyone, welcome back to TechBit Academy. Please like this video and subscribe to the channel.
Welcome back to The Explainer. Today, we are unpacking something that is just absolutely fascinating. We're going to look under the hood of the world's most powerful machines to truly understand the architecture of supercomputers. Have you ever stopped to wonder how these colossal systems combine their processing power to solve the most massive, complex problems of our time? Because it isn't just about throwing a bunch more chips at a problem and hoping for the best. It's actually all about how those chips are organized. Think about it kind of like this. Imagine trying to organize a massive team of, say, thousands of workers to build a skyscraper. If every single person tries to read the exact same blueprint at the exact same time, what happens? You get total chaos. They literally trip over each other. Well, the central problem in parallel computing is exactly this. How on earth do multiple processors share information efficiently without creating massive bottlenecks? To figure that out, we're going to trace an evolutionary journey today. First up, Section 1, the shared memory approach. Then, Section 2, distributed memory systems. And we'll wrap up with Section 3, the hybrid powerhouse. Okay, let's dive right into this. Section 1, the shared memory approach. So the absolute bedrock of this first approach is a concept called a global address space. Picture that team of construction workers we just talked about, but this time, they're all sitting together in a single communal workspace. At the front of the room is a giant shared whiteboard. Well, that whiteboard is your global address space. All the processors can access all the memory, and the real beauty here is that if one processor goes up, erases a number, and writes a new one down, meaning it changes a memory location, that change is instantly visible to every other processor looking at the board. Now take a look at how this concept is actually built in the real world. This setup right here is known as Uniform Memory Access, or UMA for short. Do you see how perfectly symmetrical it is? You've got these identical processors, those red CPU boxes, and they are all connected completely evenly to that central blue memory block. Because of this specific physical structure, every single processor has equal access and identical access times to the memory. It's a completely level playing field for everyone. But there's a pretty obvious catch, right? What happens if a worker writes a crucial update on the whiteboard, but another worker happens to be looking down at their own notes? To solve this, UMA systems use a really brilliant hardware-level feature called cache coherency, which turns the whole thing into a CC-NUMA architecture. Cache coherency basically ensures that if one processor updates a spot in shared memory, all the other processors automatically and instantly know about the update. It actively prevents our imaginary workers from accidentally using outdated information. And the best part? The hardware itself handles all of this synchronization behind the scenes. As things evolve, notice how we physically link two or more of those symmetric multiprocessor blocks together using a bus interconnect. This brings us to non-uniform memory access, or NUMA. Now, one block can actually reach out and access another block's memory, but here is the absolutely crucial difference. Not all processors have equal access time to all memories anymore. Accessing your own local blue block is super fast, but crossing that interconnect link to get to another block's memory, that is going to be noticeably slower. Just to quickly solidify these concepts before we completely change paradigms, let's stack them up against each other. Both of these share a global address space, but UMA gives you equal memory access times with identical processors clustered around one memory source. NUMA, on the other hand, gives you unequal memory access times because you're physically linking multiple SMPs together. Both are incredibly powerful setups for sure, but eventually, even NUMA hits a hard limit on just how big that global whiteboard can get. Which brings us to a totally different school of thought. Section 2, distributed memory systems. This is a completely different reality. We are officially throwing away the shared whiteboard. Notice that there is no central memory block here at all. Each CPU is paired strictly with its own local memory, and they're connected via a communication network. Memory addresses in one processor simply do not map to another. There is absolutely no global address space spanning across all these processors. Now, they're much more like independent contractors. Each one has their own private notebook, and they're communicating via walkie-talkies over that network line. And because they operate completely independently, a change that one CPU makes to its local memory has zero effect on the others. So that whole concept of cache coherency we just talked about, yeah, it totally goes out the window here. It no longer applies. But because the hardware is no longer automatically syncing up a giant whiteboard for us, a massive shift happens. The programmer takes control. When a processor needs access to data sitting in another processor's memory, the hardware isn't going to do it automatically anymore. It is now entirely the task of the programmer to explicitly write the code defining exactly how and exactly when data is communicated over the network. Synchronization between tasks becomes 100% the programmer's responsibility.
Now, you might be sitting there wondering, why on earth would we put all that extra burden on the programmer? Well, because the advantages are massive. First off, it's highly scalable. You want more memory? Simply add more processors to the network and the total size of your memory increases proportionately. Easy. Second, you get incredibly rapid local access. Each processor can hit its own memory super fast without any interference or the performance drag of trying to maintain that global cache coherency. And lastly, it is highly cost-effective. You don't necessarily need fancy bespoke hardware for this. You can literally use commodity off-the-shelf networking gear.
And that sets the stage perfectly for our grand finale, Section 3, the hybrid powerhouse. Because here's the big secret. The ultimate solution in computing doesn't actually force us to make a choice between these two philosophies. As the source material beautifully puts it, the largest and fastest computers in the world today employ both shared and distributed memory architectures. They take the absolute best features of everything we just learned today, and they brilliantly combine them. When you first glance at this hybrid distributed shared memory setup, it kind of just looks like the distributed network, right? But look a little closer at each individual node. Those shared memory components are clustered together, and nowadays they are often supercharged with graphics processing units, or GPUs, right alongside the CPUs. So inside each of these blocks, you literally have a shared memory machine. They share a local, global address space within their own little block. But then those hyper-powerful shared memory nodes are networked together in a broader, distributed fashion. It's really vital to remember how this operates in practice, though. The distributed memory component is the networking of these multiple shared memory machines. Every single machine only knows about its own memory. It has no idea what's sitting in the memory of the machine next door. Therefore, exactly like in a purely distributed system, explicit network communications are still required to move data from one machine to another across that broader network. So the big takeaway here is that this hybrid approach is the undisputed heavyweight champion. By nesting incredibly fast shared memory nodes inside a highly scalable distributed network, we effectively bypass the major limitations of both older systems. Current trends clearly show that this specific hybrid memory architecture will continue to prevail and honestly just increase its dominance at the absolute high end of computing for the foreseeable future. We've gone all the way from everyone crowding around a single shared whiteboard to a vast, globally distributed network of hybrid-fast hybrid nodes. It completely redefines what our machines are actually capable of calculating, which leaves us with one final, incredibly exciting thought to chew on. As these hybrid and GPU networks continue to scale even larger, what unsolvable human problems will they crack next? Thank you so much for joining me as we explored this explainer today. Keep learning, and I'll catch you on the next one.